Welcome now to a GCSE topic at Excel. This is topic 4, dynamic equilibrium. This is the last section of topic 4 and we will go through this for about 10 minutes. Key learning outcomes in this topic are to understand what we mean by a reversible reaction, the sign that indicates the reaction is reversible, the arrow here, which indicates the reaction is reversible, this arrow here. We will explain what is meant by dynamic equilibrium, and then we will use the formation of ammonia as an example to understand what happens in an equilibrium reaction. Okay, introduction, reversible reactions. A reversible reaction is a reaction that goes both ways. So far we've looked at reactions going one way. Magnesium reacts with oxygen, or magnesium is burnt in oxygen, it forms magnesium oxide. Now we will look at reactions where products can react together to form the reactants. We call this type of reaction reversible. So they take place in both directions, and the symbol which I've already highlighted. If you ever see this symbol here, half an arrow forward from left to right and then half an arrow backwards from right to left is known as a reversible reaction. Example, nitrogen gas from air, fractional distillation of air. Hydrogen gas, we get hydrogen gas from fossil fuels, from electrolysis of water, and that produces ammonia. The reaction is reversible. Ammonia can easily decompose to form hydrogen and nitrogen. So the forward reaction, so in our standard way, when nitrogen reacts with hydrogen, so the reactants form product, this is called a forward reaction in the forward direction. And when ammonia, NH3, decomposes to form hydrogen and nitrogen, this is called a backward reaction, a reverse reaction. So that's the first thing to pick up in this topic, that we have a reaction in the forward direction and we have a reaction in the backward or reverse direction. When the forward and backward reactions occur simultaneously, i.e. they occur at the same rate, we call this an dynamic reaction or dynamic equilibrium, we'll say. Dynamic means that the forward reaction, this one, forming ammonia, happens at the same rate as ammonia forming nitrogen and hydrogen. This is known as a dynamic reaction. So, and when the concentrations of the reactants and the products remain constant, then we reach a condition called dynamic equilibrium. In this case, another example, important example to take, is when ammonia is formed. This is known as an exothermic reaction because heat is released in this reaction. And then to decompose ammonia to go backwards, that is endothermic because heat is needed to break ammonia. So we have another terminology for you, exothermic and endothermic reactions, and we will look at this later on in year 11. Okay, so the definition of a dynamic equilibrium then, the concentrations of the reactants and products do not change, they are constant. I'm highlighting this word, they are constant. It's wrong to say they are same, so please do not say they are same, they are constant. And the rate of forward reaction is equal to the rate of backward reaction. These two conditions meet, we have a dynamic equilibrium, and we say this reaction is a closed system. Nothing goes in, nothing comes out once the reaction has started and once the reactants are mixed together. How does this image show dynamic equilibrium? I think you can work this out. Okay, this graph shows that the concentration of the reactants here is decreasing there, and red line shows the concentration of products is going up. So reactants are used up, products are formed, and can you see this horizontal area here? This horizontal area, I'm just going to highlight for you. Here. That horizontal area and this purple dotted line, this is the point at which equilibrium was established. This is the point at which both reactions, forward and reverse, are occurring at the same rate, and the concentration of reactants in the products is constant. And they stay the same, they are constant. They are not the same as each other, they are constant. You can clearly see they remain constant. They do not change now. Okay, next. Review your learning. Answer the following question. What is happening when the reaction reaches dynamic equilibrium? And when calcium carbonate is heated in an open test tube, it decomposes. Write a word equation and explain why equilibrium is not achieved. So explain why equilibrium is not achieved in question 2, and I've highlighted one key term, open test tube reaction, and you can work the rest out yourself. What do we mean by the Haber process? Haber process is a process used to make ammonia. Ammonia is needed to make fertilizers and some cleaning fluids. And fertilizers are important in order to enhance and speed up the growth of plants. So the Haber process uses nitrogen and hydrogen, which we've looked at already. There's a balanced equation for you, nitrogen and hydrogen, to form ammonia. Nitrogen from the air, hydrogen from natural gas, and the process involves a reversible reaction, as you can see from the sign, reversible reaction. Okay, so the forward reaction and the backward reaction, you can see a reversible reaction occurs when the products react to form the reactants. So use the equation to explain what a reversible reaction is. My advice is pause the video here and answer the question. The Haber process uses a reversible reaction, nitrogen plus hydrogen forming ammonia. Question, look at the equation. What tells you that the reaction is reversible? So So look at the equation. What tells you that this is a reversible reaction? I'm just going to go quickly here because the answer is on the slide. You can work this out yourself. The reaction used in the Haber process can reach dynamic equilibrium. Explain what this means. Again, pause the video and please answer it and explain what closed system means. Now, please learn these conditions for the Haber process. Temperature at 450 degrees, pressure at 200 atmospheres, and an ion catalyst. These are the optimum conditions you need to form large amounts of ammonia. The next slides will now focus on higher. If you are now doing the higher content, then you need to continue for the next part of this presentation. If you are only doing foundation, then you can switch off now. Okay. We are going to look at factors that affect equilibrium position. And this will take 4 or 5 minutes. The following things will affect the equilibrium position. Equilibrium position means, can we produce more amounts of the product or not? And what conditions will affect that? Concentration of reactants or products is one factor. Pressure of gases is another factor. And temperature is the third factor. Okay, so we will use the Haber process to explain the effect on the equilibrium position by these factors discussed in the previous slide. So the conditions used in Haber process are controlled, and those conditions I gave you: 450 degrees temperature, 200 atmospheres pressure, and ion catalyst. That will give you a maximum amount of ammonia, yield of ammonia, amount of ammonia. Okay, so what can we change in terms of temperature or pressure or concentration to make more ammonia? Temperature, pressure, or concentration. Okay, so how does temperature affect the position of equilibrium? These are the two important things you need to note. If the forward reaction is exothermic, and please note this, if the forward reaction is exothermic, then if you increase temperature, then the equilibrium will move in the opposite direction. So if the forward reaction is exothermic, you need low temperature because exothermic reactions release heat. If the forward reaction is endothermic, then you need high temperature because endothermic reactions absorb heat, so you need more temperature. So that's what happens with temperature. Now this is somewhere you've got to take a bit of time in order to concentrate here. So the forward reaction is exothermic in this case here. So if you need to increase the amount of ammonia, then because the forward reaction is exothermic in this direction, then we will decrease temperature. If we increase temperature, equilibrium will move to the left, decreasing the amount of ammonia, and there you have, and you can read this for yourself. What about pressure? When we look at pressure, we're interested in gases. And the simple concept is this. If you increase gas pressure, then the equilibrium moves to the side that has less gas molecules. If you decrease pressure, equilibrium moves to the side that has more gas molecules. Give you an example here. If we look at this example, there are 4 moles of gas on the red. There are 4 gas molecules on the left. Please look at this carefully. And there are 2 gas molecules on the right. So there are 4 on the left and 2 on the right. If we increase pressure, then because the right hand side has only 2 gas molecules, equilibrium will move in this direction to form more ammonia. And there you have your answer. What about concentration then? Well, if you increase the concentration reactants, then the equilibrium moves in the product side. It's just simple as that. So the reaction for Haber process is the following. And the reaction for Haber process is as following. And if we were to increase, what would happen if the concentration of ammonia is increased? If ammonia is increased, then the equilibrium will move to the left, forming more nitrogen and hydrogen. That's all you need to know. And there's a nice summary of this slide where you can have a quick read of what is going on. I'll just go through it anyway, and you can pause the video here to read this. If the concentration of product is increased, equilibrium will move to the reactant side. If the gas pressure is increased, the equilibrium will move to the side which has fewer moles of gas. If temperatures increase, equilibrium moves in the endothermic direction. If temperatures decrease, equilibrium moves in the exothermic direction. I need to go back slightly, and I just want to highlight something about temperature again. In the exam, you will be told that the forward reaction is exothermic or endothermic. So because here we know the reaction is exothermic, so when nitrogen reacts with hydrogen to form ammonia, this is exothermic. So to form high amounts of ammonia, you need a low temperature. That's the key thing you need to look at when it comes to temperature. Last few things then. What happens here? So NO2 is brown, N2O4 is colorless. The forward reaction is exothermic. So if we decrease temperature here, look, decrease temperature, then the equilibrium will move to the right side. What we will observe is the mixture will become pale, will become lighter, because N2O4 is formed, which is colorless. If we increase pressure in this reaction, then the equilibrium will move to that direction, to the right, because there are two gas molecules on the left and one on the right. And conversely, if we decrease pressure, equilibrium will move to the left and the mixture will become more brown. And that's it for this video, and those questions are exam style questions which you can attempt.